Okay, so chapters 4, 5, and 6. And exam would be similar to, the structure of the exam would be similar to what you have seen in exam 1. Part 1 contains multiple choice questions. This time you have 12 multiple choice questions. 12 multiple choice questions. Pardon my spellings and, handwriting there. I guess you can read it, right? Okay. And then in part 2, if I remember correctly, you have 10 questions. Uh-oh. Come on. Don't do that. I have to do that again. That screen is gone. Just died on me. Not writing everything again, guys. Exam 2, chapters 4, 5, 6. What did we say? Part 1, 12. Now onwards short form. MC. Is that okay? Part 2, 10. What? Q's should be good. Yeah. Q's. MC and Q's. Okay. Now, what is it that we need to focus from each chapter? Okay, that's what we will discuss now. So basically we will cover all the important concepts we have learned in these 3 chapters, and remember that a lot of these things are cumulative, so once you learn that, you will be able to use that in a different question also, especially a lot of things you learned in chapter 4, the mole quantities, mass to mole to mass, all that stuff comes back in chapter 6 when you do the limiting reactant problems also, right? So let us see from each chapter what is it we need to focus on. So chapter 4, mass percent. What was that? Mass percent. Percentage of any element is, if I give you the total mass of a sample and individual masses of the elements, what are the percentage of elements? So how do we calculate that? What was that equation? Mass percent of E is mass of E for any element, divided by total mass of sample, multiply that by 100. Why my pen is kind of acting weird, I don't know. After I write, it takes a couple of seconds to, show up. And that is a percentage. So that is mass percent, one of the easy questions. So I will give you the total mass and what are the elements in it. And if I give you only mass of one element, you can calculate the mass of the other element, right? Total minus whatever mass of one element is the other element's mass. Or, remember, all mass percent in a compound should add up to 100. So if you know the mass percent of one element, 100 minus that will give you the mass percent of the other element. Whichever way you do that, there would be a question on that. And then the mole quantities. Basically, you need to know mass to moles. Oh, my pen is going bad. See, it's moving around on its own. Uh-oh. Mass to moles. Uh-oh. And vice versa. Okay. What do we need? Mass to moles, moles to mass conversion. What is it that you use for this conversion? What quantity uses both of these words in there? Molar mass. Okay. So to convert from mass to moles, you need molar mass of the compound. From moles to mass also you need molar mass of the compound. So without saying, you need to know how to calculate the molar mass of the compound you are talking about. Correct? How do you do that? I will provide the periodic table. So remember, every element's average atomic mass is listed on the periodic table. You are adding up based on how many you have, okay? The sum of all the atoms in a compound that is given to you. So you need molar mass to convert between mass and moles. And one more conversion, if we have moles, we can also convert back and forth number of atoms, ions, molecules. What do we use for this conversion? The Avogadro's number. Okay, for this conversion you need Avogadro's number. You don't have to memorize Avogadro's number. I will put that on the exam. Avogadro's number will be provided. So 6.022 into 10 to the power 23 molecules, atoms, ions, whatever you are talking about. So we will have that. And then calculation from chapter 4. We had one more topic, which is molarity of solutions. So molarity is moles of the solute divided by liters of the solution. So remember that, moles over liters. I think I have put that equation. Molarity is moles of the solute divided by liters of solution in your exam booklet. So if you know how to use that equation, you should be good. Okay. Now, so without saying, if I have given you a compound and its mass, you can convert that to moles and then use moles in molarity equation. Keep in mind, molarity is moles per liter, not mass per liter. That is one of the common mistake people do. They see the mass and the volume given in liters. Oh, okay, one divided by the other is molarity. No, keep in mind, molarity you need moles. So you need to convert the mass to moles. And multiple choice question on empirical formulas. If I give you like 3 or 4 compounds, what are their empirical formulas? Empirical formulas, how do we figure out empirical formulas? No calculations on empirical formulas. It's just a multiple choice question I have. I have 3 compounds and I would ask you what are the correct empirical formulas. So empirical formulas are, what are empirical formulas? If you have the molecular formula, how do you figure out empirical formula? Yes, the atoms, the number of atoms in a molecular formula, make sure that it is in the simplest ratio possible. Not using decimal numbers, just whole numbers. So say for example, I'll write down the example right below. Let's say if I have P4O10, what should be the empirical formula of this compound? P2O5. Okay, because 4 and 10, the simplest ratio from those two numbers is 2 and 5. So that's what I mean by empirical formula. So you'll have multiple choice question on that. And forgot, after molarity there is one more calculation part we did under molarity, which is dilution. The formula we used is MAVA is equal to MBVOB, or you might have written MBVB is equal to MAVA. Doesn't matter which way you write after before. So molarity times volume, molarity of something before and molarity and volume of something after. Remember, so there are 4 variables in there and I will give you 3 of them. So you substitute the 3 of them into the place and solve for the 4th. Okay? So these are all the topics covered in chapter 4. So you have questions on all these topics either in the form of multiple choice or as a problem to do in part 2. Okay? All right, now let us go to another page and look at chapter 5. So chapter 5, we started with balancing equations. Definitely you will have a question on, not one question, I think I have a couple of equations. I will give you the skeletal equation, okay? You will have to balance the equation, okay? So balancing equations, and another question associated with that itself is balancing equations and classify the reactions. What do I mean by that? No, that is the physical states which will come under balancing equation, but classify the types of reactions. Remember we learned about 4 major types of reactions, right? Combination, decomposition, single displacement, double displacement. So when I have given you the skeletal equation, so you will balance and look at the equation and say whether it is one of the 4, okay? So that would be definitely one question, balancing equations and classifying reactions. And another question is writing molecular equation, ionic equation and net ionic equation. Again, I will give you the reactants. It will be a double displacement reaction, okay? So I can give you already that clue also. This will be a double displacement reaction which I would ask you to complete. Double displacement. So I will give you both reactants you are starting with. So you can complete the reaction. I will attach the solubility table to the exam. So you can use the solubility table and figure out which one is your solid and rest of them are aqueous. And then remember, after you balance the equation, what would you do for ionic equation? The ones that, no, before that, ionic equation is the ones that has aqueous parenthesis. Anything that is aqueous must be split as ions because it comes from the principle you learned in an earlier chapter. Aqueous ionic compounds means what? They dissolve in water and dissociate. They exist as ions. So you have to write them as ions. That is what ionic equation is. Do not split solids. Solids would exist as it is. Okay? That is ionic equation. Once you have the ionic equation, you will check what exists on both sides. Remove them, those are spectator ions, remove them and you will hit your net ionic equation. So there will be a question on that. So with that, again I think I have 1 or 2 multiple choice questions also on using the solubility table. I will attach the solubility table, you need to know how to use it. Okay? So I might ask you in multiple choice also, when the following 2 are mixed, what is the the product that is formed, whether it is soluble or insoluble. So you need to know how to use the table. What else in chapter 5? Again, single displacement reactions. Single displacement reaction, the type of question I have is, I would give you a solution and a metal, and I will ask you, if you mix these two, whether a reaction will occur or not. I will attach the activity series into your exam. This exam has a lot of attachments, the periodic table, the solubility table, the activity series, and that, ionic chart, formulas, all that stuff which you had in the previous exam also. So this would be just answering yes or no, okay? So again, you need to know how to use the activity series. That's the point here. So remember, in the activity series, the free metal will displace any metal that is below it from the solution. So you will use your table activity series and see whether the reaction will happen or not. Okay? So that will be a question. So this one, as I said, yes or no answers. That's all. Not looking for anything further on that. What else I have from chapter 5? Balancing, this thing, single displacement. What else did we cover in chapter 5? I think these are the which we covered under double displacement. I don't think I have any specific thing on, acid-base neutralization. I don't think so. No. Basically, this is the three main, because balancing equation and classifying reactions covers a lot. You need to know, the classes of reaction. What are they? How do you classify? And then writing ionic, net ionic. You need to know how to use a solubility table, how to balance the equation. See, it's all kind of, interconnected. And then single displacement reactions. I think that's what I have from chapter 5. Let me just check if I have anything else in my notes from chapter 5. Single displacement, yeah, I think that's all I have from chapter 5, okay? Well, that's all means this covers everything in chapter 5. Okay, going to chapter 6. Chapter 6 we started with mole ratios, yes. So, I will give you balanced equations for all questions in chapter 6, because every question in chapter 6 you start with a balanced equation. So I'm sorry to make the statement, I don't trust your balancing skills yet. So if I give you an unbalanced equation, ask you to balance it and then do the problem, and if you have gone wrong in balancing, therefore the entire problem goes wrong. So just to avoid that, I'm going to give you a balanced equation in chapter 6 problems, okay? All right, so mole ratios, oh, what did I write? Mole rations, look at that. Okay, yeah, I know. I mean, I've learned how to write, R like that, the small case letter R. But yeah, a lot of people have asked me, do you mean ratios? What is it? Yeah, but my V is like, I do it like that. So I have no confusion. But
yeah, me neither.
Yeah.
I started writing cursive R.
Okay, you started that. Okay. Well, mole ratios, I will give you a balanced equation. So, and if I tell you, okay, I have 2 moles of one of these reactant, how many moles of something else can form? Okay, they're only in mole scales. Everything we are just talking about in mole scales. So make sure you know that the mole ratios, how to use them, how to use mole ratios. Then another sure short question from chapter 6. As soon as we covered mole ratios, what did we learn? Well, mass ratio, mole ratio, they are all one concept. It's just that, if you are not given a quantity in moles, you will just convert the mass to moles and then do the same. But something else, if I give you a reaction and the quantities of the reactants, a 2-part question, identify limiting reactant. No, identify the limiting reactant and then calculate grams of product that would form. Okay, so it would be that two-part question. Identifying limiting reactant is the first part, and then calculating grams of the product that would form. So there will be a question like that. I think we did a couple of examples in class. So again, balanced equation is given to you. Amounts of the reactants are given to you. Okay? So how do we calculate the limiting reactant?
Whatever the number is times 1 mole of...
Not 1 mole, it comes with the mole ratio. You pick up the first reactant, whatever number of moles you have, then calculate how many moles of the other reactant you will need. Then you compare what you are given in the actual problem. Then it's logic. If you are given more than what you calculated, that means it is the excess reactant. If you are given less than what you calculated, then that is the limiting reactant. Remember that? Okay? If you need to watch the videos for those topics, please do so. All videos are posted. We are up to date on that. Cover from your book. Look at the example we worked out in class. If you want to listen or see how we did that again, go back to that video and watch. So as the concept once again, balanced equation is given to you. Quantities of the reactants are given to you. Pick up the first reactant. Calculate how much of the second reactant you need using your mole ratios. Then compare what is given to you in the problem. Then it's a logical, you have to choose limiting reactant using logic. Okay? Once again, if you are given more than what you need, that is excess, the other reactant is the limiting reactant. If you are given less than what you need, then of course that is the limiting reactant. That is the first part. Now the second part is calculating the grams of product that would form. Now comes the concept that limiting reactant determines how much product will be formed. So you will use the amount of limiting reactant to calculate the product that will form. Once again, using a mole ratio on the amount of limiting reactant. Now I have written specifically grams of product that will form. That means you have to do a conversion also there. Once you calculate the moles of the product, you will have to convert that to grams using what? How do we convert moles to grams? Conversion factor is what? What is the conversion factor between grams and moles? We already said that in this class. No? Molar mass. Yes. Exactly. Grams per mole. Molar mass. Anytime you have grams and moles, guys, without saying, remember you cannot do anything without molar mass between grams and moles. Okay? So as soon as you see grams, get the molar mass, convert to moles. Now once you have the moles, if the question is asking you to express your answer in grams, again get the molar mass, convert to grams. Molar mass. It uses both words, mole and mass. That's what connects between grams and moles. Okay, what else from chapter 6? We will have calorimetry. Q is equal to mc delta T. Last class we did that equation. Remember that? So we will have a problem like that. I will give you all information you need for water, but you will have to calculate the Q of the metal. So remember that logic. You calculate Q of the water and just change the sign for Q of the metal. Okay? Because we are assuming that on first law of thermodynamics, or energy is not created nor destroyed, or whatever energy lost by the system is gained by the surroundings, and vice versa. So we will have one question on that, similar to the examples we did on class. And one more question from chapter 6 is a very easy one, probably the easiest of all, percent yield. What is percent yield? How do we calculate percent yield? Actual over theoretical multiplied by 100%. I think that covers all your exam topics, multiple choice as well as problems. Chapter 6, so all these mole ratios, limiting reactant, Q is equal to MC delta T, percent yield, all are in part 2, all are problems. And that will come along with this. Once you calculate the Q, what is the sign, what is its significance? So if Q is positive or Q is negative, how do we say what is Q is positive means? Endothermic. Q is negative means exothermic. Yes, that will be one question, just like we did in class.
And then the specific heat is only going to be water. We don't have to know the other ones.
No, I will only going to be, as I said, this question will always be, you will calculate Q of water and then reverse the sign for the metal. So I will give you all three quantities of water, mass of water, specific heat of water, and final and initial temperature of water. So you'll have all three for water. Now remember when we did the examples in class, just to confuse you, in the question you were given mass of metal also, correct? Yes, I will also give you mass of metal. So read the question carefully before you just jump into Q is equal to MCC, MC delta T, which mass I should use in my equation. Okay? Make sure you will use everything for water and then reverse the sign. So this is what you will expect in your exam.
Have you already opened up the chapters 4 and 5 homework? So we can just...
I haven't. Thanks for reminding. As soon as I finish this class, I'll go and open it up. Okay? 4 and 5, yeah. 6 is already open, which you are doing right now. So.
Yeah, but could you open that again just so we can like...
Yeah, 4 and 5, I will go and open it back.
No, 6 too. So like after
No,
we
6
run it-
is already open. Its due date is April 2nd.
Yeah, but
So.
after we do it, can we like go back and do it again if we want?
That would throw off the, because everyone is not going to finish today. So I won't be able to do that because, yeah, I mean, you have 3 tries to do, and once you finish 3 trials, you should see the feedback. I mean, I have a question though, guys. The homework, how I have set it up is, after every trial, first trial and second trial, you should see what is your score, what did you get right, what did you get wrong, right? So that, you will have to do only what you got wrong in the second trial. But once you do all 3 trials, you should get the feedback that involves everything, like solutions, explanations, all that stuff. Do you guys actually save it somewhere? On your computer or something? Okay. Okay. It stays there, right? That's what I thought. So, but you can go back and look at it anytime you want, right? Okay, all right. I just wanted to make sure on that. So whatever homework you have done so far, which has been, past due, you can go back and look at, the questions, the explanations, solutions, everything, okay? But if you want to practice, it's like doing, yes, I can open it up so that, you can just do it again and see. Yeah, that's whatever is fine. All right. Questions on exam 2? Of course, except, what are those questions? I just told you all the questions. You just need to have the numbers, that's all, which you will get on Thursday. So, we are all good for chapter 2? Exam 2? Okay. Let us start chapter 7 then. Electron structure of the atom. So this chapter would be kind of, different from what we have done so far. Your quantitative stuff is over, if that is a relief to anyone. Okay? Most of your quantitative part of this course is being done. We don't have any more calculations as such coming up. We will be learning a lot of concepts and how do we do them. So the topics we would look at in chapter 7, we will start looking at electromagnetic radiation and energy. How do we characterize electromagnetic radiation? Then we will look at the Bohr model of hydrogen atom. We are going to look into the atomic, the modern model after that, or these two models. What we are looking at is basically what is the arrangement of electrons in an atom. Okay, and then electron configurations, basically how the electrons are arranged in an atom. We will look at some trends, periodicity, and then what do we mean by valence electrons, and we will look at valence electrons for the main group elements only. Then we will look at the electron configuration for ions, because remember, ions have different number of electrons compared to neutral atoms, and we will explore some more periodic properties of atoms. Before electromagnetic radiation, let us just start with the light that we see most of the time, mainly from sun, the sunlight, and a regular light bulb, the light that we see. It is white light, and white light is composed of different colors, and we can separate the colors in white light using a prism. Most of you might have seen that, right? When you pass light bulb through a prism, it separates into 7 colors, or you may not see all the 7 colors, but if you have a good prism and if you have done it in a dark room, probably you will be able to see all colors. And when we see a rainbow, what happens? Well, sunlight is white light, which contains all the colors, and the water droplets. When do we see a rainbow? On what sort of days we see rainbow? We don't see rainbows every day. After a rain, even after every rain, do we see rainbows? No. After a rain, when what?
Sunlight.
When sun is kind of bright, right? If it's cloudy after the rain, we don't see rainbows. So when do we see rainbows? After a rain, when the moisture is still in the air or the humidity is really high and sun is bright. So what happens is the water droplets would act like tiny prisms. And when the bright sunlight hit on it, it would separate into colors as if in a prism, and that's when we see the rainbow. Now, light is a form of energy called electromagnetic radiation, or simply radiant energy. As the name suggests, electromagnetic radiation, they have electric and magnetic fields, and we have different forms of electromagnetic radiation. Light is only one of the forms. We are going to see what are the forms of electromagnetic radiation in a few minutes. So all forms of electromagnetic radiation, they travel through space in the form of oscillating waves, and they have a constant speed, which is known as the speed of light. So these waves travel with speed of light, which is 3 into 10 to the power 8 meters per second, which is really, really fast. Okay? And when we talk about electromagnetic radiation, all forms of electromagnetic radiation, how do these forms are different? Or how do we differentiate the forms? We use these two properties of electromagnetic radiation, wavelength and frequency. So let us have a brief introduction to wavelength and frequency. Wavelength is represented by the Greek lowercase letter lambda. So this is known as lambda, like an upside down Y. And the wavelength is defined as the distance between two corresponding points on a wave. So if you look at a wave, so these are oscillating waves. If you look at a wave, usually the top curve of the wave is called crest of the wave, and the bottom curve, this point, is called the trough of the wave. So when you say wavelength, it could be from crest to crest on two adjacent waves, or from trough to trough, or let's say you want to start, like right in this point. Exactly the same point on the next wave. They are all the same. Okay? So wavelength is two corresponding points, the distance between two corresponding points. That's all you are looking at. Now usually wavelength is expressed in nanometers because these are very, very small distances. Of course, the unit is meters, SI unit for length is meter, but you will usually express wavelength of a wave in nanometers. Remember, 1 nanometer is 10 to the power negative 9 meters. So this is one of the characteristic property we would use to differentiate kinds of electromagnetic radiation. The other property we would use is called frequency, and this is not a V, this is called a nu, N-U, nu, another Greek letter, and frequency is represented by the letter nu. Now frequency is a measure of the number of waves that pass through a point in 1 second. To understand what is frequency, I'm going to use the example given in your book. Let's say you are standing on a boat deck on a calm day, and you are counting, the waves would come and slowly hit the deck, right? So let's say you are counting how many waves hitting the deck on the calm day, let's say for 5 minutes. Let's imagine you are going to stand on the same boat deck on a very windy day. And you can imagine this time the waves are going to come very frequently and hit the dock, right? So for the same amount of time, if you compare the number of waves that hit the dock in 5 minutes on a calm day versus a windy day, of course you will have more number of waves hitting you on a windy day, or we can say in other words, on a windy day the waves have more frequency. Okay? So frequency means through a point how many waves can pass through in a given period of time. That's what you mean by frequency. Now frequency's unit, the common unit is hertz, just like the car company. That's the same spelling even, right? That is how they spell hertz. Hertz, which is the same as inverse of seconds or 1 over seconds. So here is a full spectrum of electromagnetic radiation, and these are the forms of electromagnetic radiation that you would see. The electromagnetic radiation involves, G is being cut off from here. It's gamma rays, X-rays, ultraviolet, visible light, infrared, microwave, and the radio frequency. Note that the visible light, the light that we can see with our eyes, is a very small part of the electromagnetic radiation. If you look at the entire spectrum, this is the visible light. It has been expanded for you, the visible region, so that you can differentiate the colors. We can see only this much of the electromagnetic radiation with our naked eyes. Now, if you look at this one, the top scale is in wavelength units, nanometers. The bottom scale is in frequency units, seconds to the power minus 1 or inverse of seconds. So, looking at those two units, we can come up with an important relationship between these two. Note that on the top scale, wavelength is increasing in this way, meaning thereby gamma rays have the lowest wavelength and the radio frequency has the highest wavelength. Whereas if you look in the frequency units, frequency is increasing from this end, that is the radio frequency end, to the gamma rays. So what do we say? Wavelength and frequency, how are they related? What is the trend? They are inversely proportional to each other, meaning thereby when one goes up, the other one comes down. Okay? That's what we mean by inversely proportional. When we say directly proportional means when one goes up, the other one also goes up. Or when one goes down, the other one also goes down. So if two properties or two quantities you are looking at, and if they are doing the same, the trend is the same, then we will say they are directly proportional. Whereas inversely proportional means they are doing opposite or showing opposite trends. So here remember that frequency and wavelength are inversely proportional to each other. So that's what it says, as wavelength increases, frequency decreases, and note that frequency is given in units of cycles per second or 1/second or second to the power minus 1. Even though your book has a couple of examples on calculations based on wavelength and frequency, I'm not going to focus on that. We are not going to do any calculations on that. Now, here are the wavelengths of the visible light, the 7 colors which we can separate through a prism: red, orange, yellow, green, blue, indigo, violet. Again, I don't want you guys to memorize the wavelengths or anything, but you need to know what is the order of the colors. Okay? Here is a man's name which would help you to remember that order. So, whether you like him or not, we need to remember him all the time in this class. Roy G. Biv. What is Roy G. Biv says? The order starting with the highest wavelength. So, red, orange, yellow, green, blue, indigo, violet. So, you need to know that order. Okay? So, remember the name again, starting with the highest wavelength to lowest wavelength. That is what Roy G. Biv stands for. Okay. Now, so far we were talking about the wave nature of light. We said electromagnetic radiation travel through space as oscillating waves, and the waves are characterized by either by the wavelength or by its frequency. Now, the light or electromagnetic radiation also has another nature, which is the particle nature. We can also characterize light as packets of energy, small particles of energy called photons. So, photons is a name expressed to quantify the energy of light. Okay, quantify means how do you measure the energy of light? We will measure the energy of light using photons. So we already talked about the characteristics of waves, which is frequency and wavelength, and we said they travel through space with the speed of light. Speed of light is represented by the letter c. Okay, so this relationship c is equal to lambda nu. This actually mathematically explain the relationship between speed of light and wavelength and frequency. So for any wave, you will, if you multiply the wavelength and frequency, you should get speed of light. Now, note that from that equation you can derive, let's say, let me get the pen. So from this equation, if I just want to know what is lambda, what will I do? C divided by nu, or nu is C divided by lambda. Okay, whichever way you want. If you know this equation, and speed of light is a constant. So what is the advantage of this equation is, if you know one property, either wavelength or frequency, you can calculate the other, because speed of light is 3 into 10 to the power 8 meters per second, which is a constant. Now, how do we calculate the energy using photons? So, energy of the photons is, here is the relationship, directly proportional to the frequency and inversely proportional to the wavelength. So, energy of a photon is calculated either by h nu or hc by lambda, where h is another constant called Planck's constant. You don't have to memorize any of these numbers. because these are constants. You can look it up in any of the books, or if I'm asking you to to do a problem based on this constants would be given to you. Okay, you don't have to memorize the constants. So h c by lambda or h nu, not that nu is c by lambda. So basically you are just substituting that c by lambda in place of nu. So energy is calculated using Planck's constant multiplied by frequency, or Planck's constant multiplied by speed of light divided by wavelength. So if you know one quantity, that is the advantage. You can calculate the energy of that wave. Okay? All right. Here is an activity. Two kinds of light. One comes from an IR laser, one comes from a green laser. Which one has greater frequency? Red or green? The green has greater frequency. Smaller waves. So for a given, period of time, more number of waves can pass through a point, right? And of course, that means which one has greater wavelength? Must be the other one. Remember, frequency and wavelength, they are inversely proportional. Otherwise also, this is picture, so you can actually look up and you can clearly answer that. So I'm not going into the mathematical part of mathematical questions from this section in your book. Just the concepts: electromagnetic radiation, frequency, wavelength. How are they related? Okay, that's what we are basically looking at. Okay. Now we are going to look at atomic spectra. So again, when visible light or white light pass through a prism, its components separates into colors. So visible light is composed of 7 colors, so we would see it is separated into colors. And the spectrum we get is called a continuous spectrum, because it is continuous. From one end to the other end, you don't see any gap in between. From one color to the other color, it's continuous. So this kind of spectrum is known as a continuous spectrum. So sunlight, white light, they give us a continuous spectrum. But if you take colored light, such as that from a neon sign, and if you analyze the spectra, you don't get a continuous spectrum, because you would see only lines of colors at specific regions, and we call it a line spectrum. So here is an example of 3 line spectra. This is coming from mercury, this is coming from strontium, and this is the neon light, which we normally we use in those flashing signs and all that. So they do not give us a continuous spectrum, they give us something called line spectrum, because as we can see, only lines at specific colors are visible. Rest is just black. Okay. Now, if anyone is wondering, how do you produce a spectrum of an element? If you heat an element or subject it to an electric charge, the electrons in the element would absorb that energy, like the heat energy or the electric energy, and they jump into, or jump away from the nucleus, and when they cool down, or when that electric source is removed, those electrons can jump back to their original positions, and when they jump back to the original positions, that energy they have absorbed, that is being released in the form of light, and that is the light that shows up in different regions. So that is how the spectrum is produced. But what we are after is, why do certain lines appear and what causes these specific colors of light to be emitted? Or why don't we see a continuous spectrum in case of an element? Why do we see only specific lines? Another point to remember is the line spectra of elements is unique, meaning thereby each element has a unique or specific line spectra. No 2 line spectra of 2 elements, let me rephrase it. If you look at the line spectra of 2 elements, they will never look the same. They are going to be separate. Okay? So line spectra is usually called fingerprinting of elements. Just like in humans, we say no two fingerprints are the same, right? We all have different fingerprints. So just like that, line spectra is going to be different for each element. It is unique. So it is similar to the fingerprinting.
Would it also be different between like different ions of a single element? Because single elements are the same, right?
Single elements are supposed to be the same, yes.
What about when they have different amounts?
Different ions, for example, sodium ion will produce a different spectra from sodium, neutral sodium, because they have different number of electrons.
Okay.
When you say, we are just talking about the neutral element spectra right now, so we would assume, when we say strontium, doesn't matter what strontium, where it is coming from, as long as it is strontium, that is the spectrum. Okay, so in order to understand the line spectra a little more in detail, why do only certain lines appear in a line spectra? We are going to look at the Bohr model of the hydrogen atom. Okay, so Bohr model of hydrogen atom, or in other words, the line spectra of hydrogen atom, if you look at, it is one of the simplest line spectra. Of course, hydrogen is the simplest element we have, the first element with just one electron and one proton in the nucleus, and it shows only 4 lines. Okay, just 4 lines. So we are going to analyze that. Before that, a little bit, history. Let's say, do I have that slide in here? Yes. Niels Bohr, I'll go back to the slide which we didn't talk about. Niels Bohr, a scientist, he was a student of Rutherford. Who is Rutherford? We talked about Rutherford long time ago. That name is not new to you. What did he do? He did the gold foil experiment. Yes, the gold foil experiment which proved that. What did the gold foil experiment prove? Or what did we learn from the gold foil experiment? Oh my. Well, when we talked about in chapter 2, beginning discovery of subatomic particles, we talked about first J.J. Thomson discovering electrons, and then Rutherford doing a gold foil experiment and discovering that the protons are situated in the center of an atom called the nucleus. Okay, that's what Rutherford did. The gold foil experiment proved the existence of protons in the center of the nucleus. Okay, so Niels Bohr was a student of Rutherford. Now, when Rutherford proved that there are protons and they exist in the center of the atom, it was really, the scientific community at that time was not really believing it, because it contradicted the laws of physics known at that time. They were thinking, how can these positively charged particles and negatively charged particles, which are by nature supposed to attract each other, exist in the same atom but separated from each other, all protons together in the center and all neutrons, not neutrons, electrons around it. That was, they cannot really accept that fact. They just thought, why the electrons and protons are not, tumbling towards each other and just make a big, kind of a cocktail. Okay, so it was unacceptable at that time. So when Niels Bohr, with a doctoral thesis done in physics, came to work with Rutherford, Rutherford told to him, okay, you go and figure out, or you go and analyze and figure out how exactly electrons are arranged in the atom, why they are not tumbling towards the nucleus and going into the nucleus. How can they exist as a cloud outside the nucleus? So he picked up hydrogen, its line spectra, because it was the simplest one to study, and he started giving some explanations which actually made sense at that time. Okay, so he came up with this idea, or a planetary model, in which electrons orbit the nucleus in a circular pathway, just like in our planetary system, like sun is in the center and we have the planets are orbiting around the sun in circular pathways. They have specific pathways, right? Even though sun has a lot more greater attractive or the force of gravity, sun has a lot of attractive power. It's not that all the planets are tumbling towards sun and going and bombarding into sun. Doesn't happen, right? So Bohr kind of used the same model and explained this is how the electrons are existing. They are circulating around the nucleus in specific pathways, just like the planets don't leave their specific orbits, and that's why they are all not tumbling towards the nucleus. Now, this model was based on Max Planck, another German scientist, whose idea that electrons and their energies are quantized and therefore can have only certain values. I'm going back to the slide which we didn't discuss. So Max Planck, what he did was, before even Bohr started doing this analysis, he hypothesized that energy produced by the atoms, that is when they are heated, I told you, an element when it is heated, the electrons can jump to higher areas or away from nucleus by absorbing energy, and when they comes back to their original positions, they release energy. So Max Planck said that energy which is produced or the energy that is released can have only certain values, meaning thereby it has a specific, each electron produces a specific amount of energy. And that is the reason we see only lines in the line spectra. Based on, which electron produced how much energy, you will see a line corresponding to that. That's all. That was the explanation given by Max Planck. And Bohr's planetary model also revolved on this idea that electrons and their energies are quantized and they can have only certain values. So he came up with this model. This is the planetary model of Niels Bohr. So he said in hydrogen, again, here is the nucleus, which is like our sun, and these are the orbits, circular pathways. And he said the single electron in hydrogen can occupy one of the several possible orbits. These are all possibilities for that one single electron. Okay? And he labeled these orbits, the closest one to the nucleus, as n is equal to 1. The next one is 2, next one is 3, 4, 5, 6, like that. So the one that is closer to the nucleus is lower in energy, or the lowest in energy, and as you go away from the nucleus, the orbits are increasing in energy. Okay? So that means one is the lowest, and which one would have the highest energy? Number 6. Yes, that is how it is being arranged. So as it says, the energy increases as its distance from the nucleus increases, and one closest to the nucleus and increasing as the orbits getting further away from the nucleus. Now he said that single electron, based on where it was and from where it is coming down to which orbit, based on the distance covered, that electron can produce different amount of energy. Say for example, let's assume the electron was in the n is equal to 6 orbit, the one that is farthest away from the nucleus, which is highest in energy. When this electron goes back to n is equal to 2, now 2 has an amount of energy, 6 has a much higher amount of energy. So if it is going from 6 to 2, the difference of those two levels, the difference in energy between those two levels, that energy is being released. And that energy corresponds to, if you actually quantify that energy, that has a wavelength of 410 nanometers. So you will see a line at 410 nanometers which is in the violet region. So you see a line right there. Now, let's assume the electron was in n is equal to 5 orbit. If that goes back to n is equal to 2, that releases a different amount of energy because 5 and 6 has different amount of energy, right? So, you can even just numerically think of this. 6 to 2, the difference is 4, whereas 5 to 2, the difference is only 3, okay? So, that difference corresponds to 434 nanometers, and you will see a line exactly right there. What was that? Okay, all right. Similar. Let me just finish this. I know Sandra is having a big question mark on the face. We will look at that. And then similarly, n is equal to 4 to 2 will have a different amount of energy that corresponds to 486. 3 to 2 will have a different amount of energy which corresponds to 656. And Bohr said if an electron is going to n is equal to 1, okay, so 6 to 1 will have the highest energy gap, right? That is such a high energy which is not falling under visible region, which will fall under UV region, and that's why we don't see any lines. Or let's say something goes from n is equal to 3. It's not as big as n is equal to 2, so this will fall in the IR region. Again, we cannot see that. If you look in the electromagnetic spectrum, what is before and after visible region? UV and IR. Okay? So he said when the electrons jump from the higher orbits to n is equal to 2 level, whatever the energy they are releasing, that will show up only in the visible region, and we will see the 4 lines based on what is the amount of energy released. This was Bohr's model, and it made sense, and they accepted at that time. Sandra's question.
All right, I guess I'm getting stuck on, right, starting with the first one, when n started on n was 6 and went to n was 2. I guess I'm thinking in distance.
In distance.
I don't know why.
Okay.
It's the furthest away.
Yes. Okay.
But it's the lowest nanometers.
Yes, how energy and nanometers is related. Let's just go back to this one. Yes. Oh, not this one. This one. Energy is inversely proportional to the wavelength. So, lower the wavelength, higher the energy is. Okay? Energy is directly proportional to the frequency. Higher the frequency, higher the energy. But frequency and wavelengths are inversely proportional. So, lower the wavelength, higher the energy. So, get that relationships first before we analyze. That is why we talked about this slide, even though I'm not doing any problems. I told you, why did we show up, why did we show these equations and why did we look at it? Just to get that idea, okay? So, frequency and wavelength, they are inversely proportional to each other. Now, let us see how energy is related to each of them. Energy is directly proportional to frequency. So, if you have a higher frequency, you have high energy. Higher the frequency, higher the energy. But energy is inversely proportional to wavelength. So, lower the wavelength, higher the energy. Now, after we said that, look at this one more time. Now it makes sense, correct? 6 to 2 should be the highest energy gap, which would show up as the lowest wavelength. Okay, that is why. So, this is what Bohr said. That is why we see only lines in line spectra, and it made sense. It was very good. So, this is again showing what we just discussed. When electrons move from a higher energy orbit to a lower energy orbit, it loses energy, which is basically E final to E initial, where it was and where is it going, that difference. Delta means difference again. So, this delta E will be the same as the energy that we see on the spectra, okay, where it corresponds to. So this energy is released as photon, and the photon will show up on the line spectra. Now, there were deficiencies in Bohr model because it explains only hydrogen atom and its spectrum. When Bohr was given, let's say for example, iron with 26 electrons, he really could not explain what is going on. He could keep track of, one single electron in hydrogen, where it is coming back, and therefore where it is, how much energy is released and where it would show up in the line spectra and all that. But all atoms in general he could not explain, so we needed a more complex model which would generalize everything. But this actually is the foundation, the stepping stone for us to develop the modern view of atomic theory. Okay, we took a lot of ideas or points from Bohr's model, and we developed the new model of atomic theory, which is known as the quantum mechanics. So this quantized behavior of the atoms, that was later better understood during the time of Einstein and others with the quantum mechanics, but this is where it all started. Okay, let us have a clicker question. It's going to be an easy one, guys. Here is the question. In the Bohr model, which of the following electron transition will result in the emission of highest energy photon? I haven't started the clock yet. So remember the Bohr model. Look at the picture if you want in the book. Which one will have the highest energy photon? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All of you have clickers today? Okay.
So that last comment from the last slide about like Bohr laying down the foundation and quantum theory stepping up, does that mean that from element to element, a Hawk like 6 to 3 would have slightly different?
Yes. And we will look into that. We are not going to the details of quantum theory or quantum mechanics, but we have the introduction to that in coming slides.
Cool.
So we will have a generalized, explanation on why from each element to each element, why it is different.
Yeah. Too bad about that as quantum mechanics, huh? We almost had it.
I know. Well, from the works of earlier scientists, newer theories and quantum mechanics is still an active area where a lot of research is still going on. It's not completely understood yet.
Yeah.
So something is going on. What is it? Overthinking it. Yeah, probably. Probably you are overthinking it. We are not done quantum mechanics yet, guys. No overthinking. Did everybody answer? All 21 from here, right? Okay. Which one is it? N is equal to 6 to, N is equal to 6 to, N is equal to 3? 5 to 3? Why? Answer should be A, 6 to 3. Oh, let me just, wow, I have a, well, still majority of. Let's just look at that picture one more time, guys. That's why I said look in the picture in your book. Here is the picture again. Who has the highest energy? Who has the lowest energy? 1. So you got the order. 1, 2, 3, 4, 5, 6. As you increase the number, energy is increasing, right? So when somebody goes from 6 to 3 or 5 to 3, which one has the larger difference? Larger the difference, larger the energy. 6 to 3.
Yeah, I'm on her. I'm on
See.
you because when she asked you, when I asked you, you said it was inversely proportional.
That is wavelength, right? Am I talking anything about wavelength here? I am asking which one would produce the highest energy photon. That's all I am asking. Which should be again right here. Look at this. Energy of the photon is what? Delta E, or the delta means difference in numbers. So higher the difference in numbers, higher the energy. What your question was, why am I seeing lower numbers for wavelength? That is just wavelength numbers, not energy numbers. Okay? See the difference? Is everyone clear on this one? Okay. So it's just energy is absolute value of delta E, meaning thereby if you have 6 to 3 or 5 to 3, which has larger difference, of course 6 to 3, right? So that should give you a larger energy photon. Her question was why it is showing up in the lower wavelength if it has the higher energy, and I said energy and wavelength has an inverse relationship. Okay, let me see what we are doing. Well, the modern model we will start after the exam. So we will stop right here.